Let's apply what we learned about the first law of thermodynamics and its application to engines.
You
Problem
lose.
2 is loaded with information. Okay, when we looked at the first law, it was about energies. It was about heat. It was about joules. So I'm giving you temperatures in this problem. You're seeing Kelvin. You're seeing Kelvin. These are temperatures. Okay, this is the high temperature reservoir. So this is TH. This is the cold reservoir temperature. This is going to be TC. But folks, that wasn't in the formula. That wasn't in the first law. The first law is about the heat. So let's focus on the heat. When the engine is running, it extracts from the hot reservoir. So let's draw this picture, right? Here I have my hot reservoir, okay? Here's my engine. Here's my cold reservoir. It's pulling from the hot reservoir, so 400 joules is going into it.
Most impressive.
The engine itself is doing 250 joules of work out. The question is how much energy is being expelled to the low temperature reservoir. They're looking for that. Well, QC is going to be QH minus the work. If I do the 400 joules minus the 250 joules, it is simply 150 joules. It's nice, folks. There isn't any fancy algebra. It's just like what adds up to it. The end. Okay? It's kind of nice. Kind of nice. Part B. I would like you to try this out. So go ahead and pause me. Pause me. Try it out.
You lose.
So once again, we have a very similar setup. We have 10,750 joules coming in, right, as input. It pumps out 2,420 joules of work. The way to solve these problems, folks, is to always draw a picture. See where the energies are going. See where the heat is going. See what goes where. See what's missing. Allow arithmetic to do the rest for you. Okay?
You win.
Remember that first law is going to be delta U is Q minus W. We associate delta U with the temperature. So based on the first law of thermodynamics, a few ways that we could reduce the temperature, right, would be to make it so that the work, right, we could make the work equal 0. We could reduce the temperature by removing heat. So if we were to look at this instead as an engine, if we were to look at it as QH is equal to QC plus W, we would be noticing that if we wanted to go ahead and reduce the temperature, we could increase QC, okay, or we could decrease QH. And one of the best ways to decrease QH, or heat, right, the best way to reduce heat is to make it negative. How do you make negative heat? You cool things off, okay? So, few observations we make using the first law. Problem 4 is a little, problem 4 is a little deep, but it's not too deep. So I wanted to show you some special cases.
I think I need a hug.
We have some. There are more than just these 3, but these are the 3 that are more approachable for conceptual level physics class. We have isothermal processes, isovolumetric, and adiabatic. Isothermal is when the temperature is the same. Now remember, if the temperature is the same, the temperature is related to the internal energy. And so the object's thermal energy, the delta U, would be 0. If the change in temperature is 0, delta U would be 0. And remember, we're looking at the first law. The first law is telling us that delta U is Q minus W. So if delta U is 0, right, because the temperature is the same, then I can move the work to the other side, and I end up with that heat is work. So heat is work in this case. Okay, so if the temperature is staying the same, and I am not changing the thermal energy of the object, then the work is the heat. Okay. This usually in real life, balloons are a good example of this. Okay, we're not changing the temperature of the balloon. We're just going to go ahead and add some heat, right? It absorbs the gas absorbs the heat. It expands the balloon, and then we end up doing work on the balloon because it expands. Isovolumetric is also known as isochoric, and it means that the volume stays the same. So imagine if we're trying to heat up a balloon but it doesn't expand. Okay, if it doesn't expand, there's no displacement. That means the work is zero. And what happens with my first law of thermodynamics, we have Q minus W. If there's no work being done, then the work is zero, and we end up with delta U is equal to Q. So we end up with the fact that the change in the thermal energy is the same as the work. Okay. And then finally, if it's adiabatic, adiabatic means that the heat is zero. There's no heat being added. So if we look at our first law, right, delta U is Q minus W. If Q is zero, that's gone, and we get delta U is equal to negative work. Okay. Now the negative is, remember when you look back at the last video, when we looked at our definition of the first law of thermodynamics, if it's minus, it's work that's done by the object. If it's positive, it's work done on the object. Okay. In our case, we're not too concerned about those details. So just be aware that in this case, if it's adiabatic, if the heat is zero, then the thermal energy, or the temperature, is going to be related to the work that's done. Okay, so the thermal energy, the change in thermal energy, is going to be based on the work. Problem 5. A balloon is filled with a gas and absorbs 115 joules of energy. The balloon expands but stays at the same temperature. This is isothermal. We just talked about this. In an isothermal, delta U is equal to Q minus W. In an isothermal process, the delta U is zero because the temperature is it's constant. Okay, which means I get Q is equal to W like we showed previously. So this problem is pretty much done. The heat is 115 joules. Therefore, the work done on the balloon is the work done by the balloon. Is going to be 115 joules. Okay. For your summary, does heat create work, or does work create heat, or do both happen? Explain or give some examples.